Hi, and welcome back to Codex. Our talks this summer feature graduate students and postdocs who are nominated to speak by their senior colleagues. Today, we have Marc Christian Zimmermann from the University of Cologne. Marc is a postdoc working on discrete geometry and spectral methods in combinatorics. We are happy to have him here today to tell us about critical lattices and the Gaussian core model. Take it away, Marc.
Thank you, and I'm happy to be here. Thank you for the invitation and the possibility to speak about something I really like, which are lattices. This is basically the first object that really made me want to stick to mathematics when I was a student, and I still like it. So this was a bit of a longer project. We had basically over all of the COVID lockdowns in Germany. It involved a PhD student in our group, Arne, who just defended his thesis earlier this year, and two master students, Aurelio and Antonia, as well as the head of our group, Frank. And there's the key. So what I will tell you about today is in the context of energy minimization for lattices. What I want to do eventually is find a local maximum for energy minimization, which sounds a bit contradictory at the beginning maybe, but it wasn't our question, and we just tried to help some people out. We really tried to do that, but in the end, we ended up doing a lot of other things that did not provide local maxima, but still were, to us, fun stuff. And I will try to tell you a little bit about this. Then I will try to come back and tell you what is hard about finding a local maximum. And with a little cliffhanger here, maybe we will find one, maybe we won't. If I get through cleanly, maybe I can give you an outlook on a current project that is somewhat related to energy minimization, but different in its own right. I have said that I like lattices, and I should maybe remind you what a lattice is, or if you haven't seen it before, tell you what it is. So for me, a full rank lattice is a discrete subgroup of the Euclidean space of dimension m. I assume this to be full rank. Just for technical reasons, it's not really a big thing. In any way, you could just take the vector space spanned by the lattice and consider it to be a full rank lattice in this vector space. People working with lattices usually use one of two parameterizations to write lattices down. Either you choose a set of linearly independent vectors in R to the n, say a basis, if it's supposed to be full rank, and you take all integral linear combinations of these vectors. This is precisely what gives you a lattice, and you can write this nicely by using a matrix, invertible n times n matrix over the reals, and just write L to be the matrix applied to all integral vectors in R to the n. Another common parameterization, which is useful pretty often, is using Gram matrices. And this is just, we choose any basis of the lattice, anything of this type up here, and we take its transpose times itself. So we collect all inner products between lattice vectors, basis vectors of the lattice, and we can compute all inner products between arbitrary lattice elements from this. This, of course, is a positive definite matrix if the lattice is full rank. Otherwise, it might, no, this is always positive definite. And it is by far, it is not unique, not by far. Even the basis is not unique. But if you have any two bases that give you the same lattice, they are, of course, related by some element, which is an integral matrix, which is invertible over the integers. So there's a really nice group acting on different bases of the same lattice, and you don't have to actually worry about this all too much. I'm only telling you this because in what follows, I will assume our lattices to, geometrically speaking, have point density 1. I would say that the determinant of the lattice is supposed to be 1. This was more number theoretic. This just means that the absolute value of any basis of the determinant of any basis matrix is 1, or the determinant of any gray matrix is 1. If I would try to draw a lattice, it would look something like this, a bit crude. It's supposed to be super regular and super symmetric. It kind of is, I hope. It's just a set of points spread throughout the whole space very evenly. And what I just showed you was to basically write a lattice like this. I take two vectors that span the lattice, say v1 and v2, the purple ones. And I say L is just the result that I get if I take this matrix times z squared. And the condition that we have point density 1 translates to this fundamental parallelotope to have volume 1. So in a geometric sense, if you take something of volume 1, you should find one lattice point in its inside if it's not put in a very bad place, so to say. Okay, so this is the geometric setup, the object that we are looking at. And what I want to do is I want to associate some notion of energy to a lattice. For this, I take a full rank lattice. I take any non-negative function defined on the positive real numbers, and I associate potential energy depending on F to the lattice L. If you have seen energy for other point configurations, this might look a bit strange because we don't take really interactions between pairs of lattice points, but only lattice points and their interactions to the zero vector, the origin of the lattice. This is because for lattices, we can do this, and this is just the same object. And we will just not worry about this, but prefer this term because it is a bit simpler. I don't want to do this for arbitrary potential functions F. I want to do this for Gaussian potential functions for various reasons. Maybe the first one, if I just do this, the energy looks a bit nicer because this function here is now just an exponential. We have the squared norm of a lattice element up here and some parameter alpha that basically decides how fast the Gaussian descends, decreases. In physics, if you would do these kinds of energy types seriously, which I don't do, I just take the problem. I like it because it involves lattices. Then you might say that Gaussian potentials are a good choice. You might also want to consider inverse power laws or something of this sort. And then there's a mathematical fact in the background that if you would take any completely monotonic function, like a Gaussian or like a Rees potential in inverse power law, you can write this as a convergent integral over actually the Gaussians. So these are in some sorts the extreme cases you have to look at. And we'll start by looking at these extreme cases. From now on, I would like to more or less leave all intuition behind and just do some mathematics with this. Maybe one picture to illustrate why this problem might be a bit complicated. What we do is we sum over all lattice points that are not a zero vector. And depending on the distance of a lattice vector to the origin, there's a bit of force we need to apply to a point, say. I think the intuition behind this is we would expect the points to be repelled by the origin, and we want to hold them in place, and we need to decide how much force we have to apply at a point to keep it still. The closer the point is to the origin, the more force we need. And now our problem in computing energy is that we sum not only over these short-range interactions, but we also sum over interactions with points that are far spread away from the origin. And this can make the problem super complicated because we have a series and some stuff gets a bit harder. Oh, sorry. If you have not seen energy minimizations for lattices before, but you are familiar with lattices, you might think that this looks a little bit like sphere packing if we forget the long-range interactions, and it actually does. If I would supposedly take a Gaussian with a very high alpha parameter, so I would let alpha tend to infinity, then only the contribution from the shortest vector of the lattice will matter. This is because then the Gaussian just dampens everything out that happens farther away. And the only thing we need to actually say something about this is to know how big the smallest distance of any lattice point to the zero vector becomes. And if I would now draw a sphere packing, it's exactly the same situation. I try to pack these blue spheres, which aren't really spheres in this drawing, but I hope this is okay. And I just take a look at those lattice points which are closest to the origin, and I see that if I don't want these spheres to overlap, I can make them as big as half this distance. So again, the same invariant, only the shortest distance is relevant. So what makes energy minimization harder than sphere packing in some sense is that if I don't only have to take into account these short range interactions, but long range interactions, the problem can become fundamentally different. Why do I talk about energy minimization when I only have defined energy? That is because there is an optimization problem in the background of this. And what we are interested in is the global and local analysis of the function of associating to any lattice L of rank n with point density 1 its energy for some fixed Gaussian potential. So this is a function on the manifold of rank n lattices of point density 1. And this can be just tackled like any other textbook calculus problem, albeit it's high dimensional. And the usual questions arise. First of all, if you want to talk about minima in any kind of way, you might like to determine first whether anything is a critical point on your manifold. So when is a lattice critical? This we will talk about today. What we won't talk about today, but which is completely astounding to me, is that there is a notion of locally or universally optimality of lattices. You can also drop the local here and make it global universally optimality. Works the same way. We say that something is locally universally optimal if it is locally optimal for any given Gaussian potential function. So it has to simultaneously be a minimizer for all of them. That this is possible, that these things exist, is to me some kind of miracle, and they only exist in certain cases. We don't know a lot of them, but we even know of global universally optima, namely the lattice E8 in dimension 8 and the lattice, the Leech lattice in dimension 24, which are also the best known sphere packings among their dimensions, not only among lattices, but in general. And these results by Henrik Kohn, Marina Wiazowska, and their co-authors, I think were some of the bigger mathematical results of the last years. And Marina got a Fields Medal for this, so this has to mean something. We won't do this kind of hard mathematics today, but now I come back to what I actually want to do. I wanted to discuss with you how to find local maxima for this function. So you might wonder why we wanted to do this. And this dates back to 2020, just before COVID hit. Frank and I were at a workshop in Berkeley, where Noah Stevens Davidovitz asked precisely this question: do these local maxima exist? And he did it for a good reason, I think. They had a nice result. They had a nice proof for it. It was really short and elegant, but this proof assumed the non-existence of local maxima. Nobody knew if they existed. So they came up with a more involved, more complicated, longer proof. But they still wondered, do we actually need the longer proof, or can we return to the short proof? We tried to answer that question for them. Frank and I had a good idea at which lattice to look at. We started computing right away. We had a good idea how to do the computations. And what should I tell you? It worked out very easily. We had some very nice numerical computations. Everything looked super fun. And we had found our local maxima. At least for a little bit. We'll get back to this at some point. Because what happened is we checked our computations when we tried to make everything rigorous. And as you would suspect at this point, if you have ever done any computations yourself that just work out perfectly the first time, they don't work out perfectly the second time you do them. And there were not some numerical imprecisions in the first computations, and we had to start back over again at zero. But we were stubborn and we thought maybe we looked at the wrong object, but we looked at the right idea. And our idea was to look at even unimodular lattices. So if you never heard of this term, unimodularity says that a lattice is equal to its so-called dual lattice, which is a number theoretic term, I would suppose. It's not so much geometric. You take all vectors of the ambient vector space that have all integral inner products with all lattice vectors. So this comes from number theory. This immediately implies that L has point density 1, so it is good for us. And actually, for a lot of geometric problems, this number theoretic property seems to be an indicator that the lattice will be somewhat good for it. I guess coincidence, maybe not. Lattice is called even if the squared length of any lattice vector is an even number. Now, even unimodular lattices do only exist in dimensions that are divisible by 8. There's a unique such lattice in dimension 8. If I say unique, I mean up to isometry of lattices. Of course, there's some equivalence notion. I guess fine. There are 2 such lattices in dimension 16, something that is called D16 plus, part of the bigger series. In dimension 8, it's actually E8, and the orthogonal sum of E8 with itself. In dimension 24, curiously enough, there are precisely 24 even unimodular lattices. There's the famous Leech lattice, and there are 23 other lattices, which are called the Thiemeyer lattices, according to the guy who found them. From dimension 32 on, the situation becomes a bit more unobservable because we know that there will be at least 80 million such lattices, but nobody knows how many there are. We decided to take a look at these 23 guys, the Thiemeyer lattices, which are in dark pink here. Before we do this, I think we will discuss a small example of a unimodular lattice that maybe you have seen. If not, you have seen it now, which is nice enough. It's the E8 root lattice. This is even unimodular. You can just write it down with this parametrization. You take all vectors that either have all integral coordinates or all half integral coordinates, and you require the sum of the coordinates to be an even number. This is a very simple set. It's a nice lattice. It's the best sphere packing you can find in dimension 8. What's nice about this lattice too, which we will lose in dimension 24, it's generated by its vectors of squared norm 2. I've written them down here. You can take all permutations and sign changes of these vectors here with exactly 2 1s or minus 1s at any place, or you can take this vector consisting of 1/2 as long as you take an even number of minus signs to make this condition above here be fulfilled. We will talk a lot about elements of squared norm 2 in lattices. They look something like this, and there are some nice structural results about these sets of lattices. So, haven't seen one such lattice. I would like to tell you how we will have to look at lattices in the rest of the talk. And I'd argue that we should think of a lattice as an onion. We have something in the middle, the origin, and then we build up the lattice layer by layer. We have those points that are closest to the origin on the purple sphere. We have points that are a bit farther away on this blue sphere, and then even farther away on this yellow sphere. And at some point, these spheres started to look nothing like spheres, so I stopped drawing them. But this goes on for all of the time. Any such sphere that contains any lattice points, I will call a shell of the lattice. Now, if I fix which squared norm I expect the points to have, I write L of M. And these shells are deeply connected to the so-called theta series of a lattice, which we now take a look at closer for even unimodular lattices. This works in general, but everything we will do will not work in general. So from now on, really keep in mind that we have an even unimodular lattice. The theta series is defined as a sum over all lattice points of some complex Gaussian times the squared norm up here. And we can rearrange this sum by just saying, well, this depends only on the squared length of x. I can just say I suspect my x to have squared length 2m. Stay with me for a second. And then count how many points of squared norm 2m I have. And I call these am. This shift here, that the index is m, but I apply 2m, is a bit unfortunate, but it's good practice in lattice theory, and I did not want to reinvent the wheel here. this has reasons to write this thing nicely analytically. We don't need to get into it. Just don't wonder that a 2 appeared here. It's just to base out this fact. But this now is a series, a fairly easy series, some Fourier type series. We have some coefficients, and these coefficients actually tell us how big the shells are. Now, if this function would miraculously be analytically tractable, we would be able maybe to obtain information about the coefficients just from this analytic object. And this is precisely what will happen. What is nice also is that if we take a look back at how we defined energy, this also only depended on the squared norm of the lattice vectors I put into the function. So I can rewrite it the same way. The same coefficients appear that come from the theta series. Just this term looks a bit different. There's no I in it. But this is actually just the value of the theta series of L at a certain point in the upper half plane, minus some constant, not important. And this actually is where we can leave all physics and energy behind. We will talk about theta series from here on out to us for the most part. Why do we do this? Why is this object nicer than this object? The reason is that if L is even unimodular, this theta series as a function in the upper half plane is a modular form. So it's supersymmetric. There's a ton of theory about such objects, and you can basically look everything up you want to know. In particular, this will give us very nice bounds on the coefficients. Even if we don't know the lattice completely, we can at least bound how many points of a given square distance there are in the lattice. Another nice aspect that helps with energy minimization is that the so-called theta transformation formula holds. And this is basically Poisson summation formula applied to the theta series of L. So this is just some harmonic analysis, very basic. But what is nice about this is that we only now have to consider Gaussian potentials where the parameter is at least pi, because if we would be smaller than pi by this change, I mean, then this is the same lattice if it's unimodular. Then we just have here like a point of symmetry, and we can say, we already know what happens. So we only have to look from some point onwards, and we don't have to worry about alpha becoming arbitrarily small, only arbitrarily big and somewhat big around pi. We will now investigate the problem shell by shell. And in this big sum, the series will be divided into an infinite number of finite sums. And for each finite sum, we will be able to use the theory of spherical design to derive results. Now, what is a spherical design? I guess this is more along the lines of what is talked about here usually, I guess. I repeat it nonetheless. A finite set living on some sphere of some radius r is called a spherical T design. If whenever I take a polynomial that has degree at most t and integrate it over the sphere of radius r, then this value of the integral is just the average of the polynomial evaluated at the points of the design. So this is sort of making integration a lot easier. It's just summation. We will be interested in spherical 2 designs. And if X forms a spherical 2 design, then among other things, the following identity in pink holds. And I've been told that in the language of codex, I should probably say that this is something that you would know as a tight frame. And that is true. But even though tight frames are also very nice objects, I will stick to the term 2 design for the remainder. And you can think of it any way you want. We will actually not need much more than this identity going forward. The nice fact is that if L is even unimodular lattice in dimension 8, 16, or 24, then all shells form spherical 2 designs. So this identity will be available for use if we have a need for it. And this is why we started to look at these lattices, because we knew this. And we knew that this should make our computations a bit easier. Now, I said before, I want to determine criticality of the lattices, determine whether they are local maximum or local minimum or stuff. And I will do this just as in high school, just a bit more complicated. I will just take derivatives, the gradient, the Hessian matrix. I will look if the gradient vanishes, and I will look at the eigenvalues of the Hessian. To do this mathematically, I go to this manifold, the determinant one surface in the cone of positive definite matrices. We just chose to parameterize lattices by Gram matrices. Then we have these objects. And since we want point density 1, we had to fix the determinant. Now, this has a nice manifold structure, and you can explicitly parameterize the tangent space of the identity matrix. This is just a set of symmetric traceless matrices. So all tangent vectors are super easy to work with. And I have to fix some notation going forward, of which I hope you're familiar with it. If not, you have to become familiar with it now. I will write shorthandedly something like matrix square brackets some object for this value of this quadratic form. So I take some object x, I evaluate x transpose hx. This is a quadratic form in x, and I write it shortly like this. Also to have Euclidean structure of some sort on my space of symmetric matrices, I take the usual inner product on this space, which is just the trace inner product. I take the trace of the product of two matrices. If you would embed this space in the obvious way into Euclidean space of dimension n squared, this is just the Euclidean standard inner product. You can see this by just writing down everything in coordinates. Now, I would like to forget the analysis as fast as possible, but we can't. We have to take a closer look at the gradient, for example. And the gradient satisfies the following equation. This, fortunately, has been known for quite some time. Renaud-Coulangin and together with Achel Schumann figured this out, wrote it down. We just had to take a look at it. We knew this would exist. So there's a nice expression to evaluate the gradient. We can write this as a sum over all lattice points, or again, which we will do anytime we have the possibility, we can arrange this shell by shell. So I don't care what the R's are that can appear. The set will be empty most of the time, but sometimes it's not empty. And then we have a nice finite sum over some lattice shell over here. The nice thing is, if all shells of L form spherical 2 designs, then we immediately can deduce from this that L is critical. This is just by rewriting this sum here in the standard inner product. We just have to note that this expression actually is this inner product. From an easy exercise if you have not seen this before. And then we use the fact that we know that this is just a multiple of the identity matrix by some constant, namely this constant. If here is the identity matrix, then this is just the trace of H. So we find that everything is 0 because H is a tangent vector, and this is a traceless matrix. So whenever we do this, L is critical, and this in particular holds for all 8, 16, or 24-dimensional even unimodular lattices. This is nice. So far, so simple. It becomes more involved if we go to the Hessian, and I am afraid we will do this. It looks somewhat similar. It's a bit more complicated. We now have 2 of these guys over here. I again rewrite this by shells. And at this point, when we tried to evaluate this, we wondered about this guy and this guy here separately. One of them is nice, the last one, because as a polynomial in X, this object is of degree 2. This here, as a polynomial of X, is of degree 4. Now, if you only assume to have 2 designs, you might believe that this guy here becomes easy to handle. Because if we have 2 designs, polynomial of degree 2, we will be able to do something. Degree 4, this is more involved. And this is really more involved. This is the main technical contribution, I think, of the paper. and computations involving this guy span numbers of pages, which I won't go through with you, but I want to show you what we actually know about this. Because even if it's not super straightforward, it wasn't all too hard to actually compute the eigenvalues of the Hessian explicitly, more or less. And since we know now that all the lattices are critical, this is the only information we need. So from now on, I'm only interested in computing eigenvalues of some Hessian that we have just seen. The big picture is that if L is even unimodular and at most of dimension 32, then all eigenvalues of the Hessian are actually only dependent on this very simple, very finite quadratic form. This is a quadratic form that takes as argument a symmetric traceless matrix and associates to it some number by summing over all vectors of squared norm 2 in the lattice. This is the bad polynomial, the degree 4 polynomial. This is what you should take away from what I'm telling you at the very least. If you know the eigenvalues of this object, which is finite and nice, you know the eigenvalues of the Hessian. I can make this explicit, and I fear I will show you how to make this explicit on the next slide. It looks messy, but it's actually nice enough. So we need a little bit of notation to make this completely precise. Under the assumptions up here, we fix again the notation for the theta series of the lattice L. It has coefficients AM, and we have to involve another object, which is a special modular form, a so-called cusp form, because in this Fourier expansion, the constant term vanishes. That has a certain weight, and for which we normalize the first non-zero coefficient to be 1. This is auxiliary, but we needed to write down the theorem, because if you have this notation fixed, all eigenvalues of the Hessian are just given by these series expressions down here. And as you might see, these are two summons. This one is coming from the degree 2 polynomial, the nice guy. This one is coming from the degree 4 polynomial in the decomposition of the Hessian, the not so nice guy. I said that in the end, the eigenvalues only depend on the eigenvalues of this auxiliary quadratic form, Q of H, and they appear only up here. I tried to make this a bit colorful, this pink lambda. This is the only point where something happens. Everything else is completely determined if you fix the lattice. These are all constants you can compute away. You only need to know all of the possible lambdas that this Q of H gives you. And this still is some work. But even though I will not tell you how we did this in detail, I want to show you that these eigenvalues are actually super nice numbers. Okay, so the story so far, we in principle know the eigenvalues of the Hessian as soon as we know the eigenvalues of this quadratic form. This quadratic form only depends on the vectors of length 2 in our lattice L. So how do we compute these eigenvalues of this quadratic form? We do this by using a little bit of structure we know about this set. If you have never dealt in your life with root systems, the next two lines will not help you very much. But what happens here is that this set is superstructured. It is in dimension 24, either empty, then you have the Leech lattice, no vectors of length 2, or it is big enough to generate the complete ambient space. We saw this for the E8 lattice, where it generated the complete lattice. Here, it will not generate the even unimodular lattice, but something smaller. But as a vector space span, it will be the complete space. And we can actually pin down how these sets look. These sets are orthogonal sums of irreducible root systems of certain types. If you have seen them, you already know that these are highly structured and there's a lot of mathematics you can do with them. If you have never seen them, maybe you can believe me that this gives you a clue that this set is actually nice. There's a lot of stuff you might be able to do this, to work with this, and we actually were. So in the end, whether or not you believe me, what we have to find out is what happens if you sum over some irreducible root system instead of these vectors of length 2. We have to replace the object we sum over up here and then decompose stuff. And this is what we did. For each irreducible root system of one of these types, geometric nice objects, we were able to compute the eigenvalues of this quadratic form. And even though it's a bit of text, I just want to show you that if you do this, you get very nice numbers. These are strictly positive whole numbers. They are very structured. We know the eigenvalues, we know their multiplicity, we even know the eigenspaces, we can pinpoint everything down. And this only works because these sets are super nice. What we do is we use representation theory of a group associated to these root systems, the Y group of the root system, and just X everything through, and it works out nicely. This is not your cup of tea. You at least see that these numbers are super nice. And also for the exceptional cases, E6, E7, and E8, they are super explicit. So we have all the information you would ever want to have, and maybe more, I'm not sure. But everything worked out super nicely at this point. The question now remains, if we in principle know the eigenvalues, have we found a local maximum? This is what we try to do. And the answer is, of course, no. While we did a lot of interesting mathematics and we are now able to compute a lot of these eigenvalues for the Hessians of even unimodular lattices, unfortunately, none of them turned out to be a local maximum. I will show you briefly why in this case. This is just a repetition from the theorem with the ugly formulas from a few slides back. And this is just the first summand of each series. And then we have some higher order terms that we forget for the moment. And we assume that alpha becomes very large. Because if alpha becomes very large, these higher order terms, they don't matter. The exponential function will dampen everything out. And in fact, only this object in front here will determine the complete sign of the eigenvalue. If lambda is strictly positive, then this will become big enough to dampen this out, and it will be strictly positive, which indicates something like a local minimum instead of a local maximum. And if lambda is 0, then this is no longer here, and this thing will make everything negative. Now, we have only 2 cases we have to consider for the Thiemeyer lattices. The first one is that the system of roots, the vectors of squared length 2, is an irreducible root system. It's of one of these types, whatever these are. You can just take a look at the list, 2 lattices appear. But if that happens, our theorem from 2 or 3 slides before just becomes applicable. These are integral whole numbers positive, and all lambdas are positive. And therefore, this will, at least for large alpha, make everything positive. And all eigenvalues of the Hessian we were interested in the beginning are now positive. So local minimum, not a local maximum. For the other 21 Thiemeyer lattices, the root system is reducible. That is a sum of at least 2. Say this specific sum, you could take any other sum you like. As long as you have a sum of 2 irreducible components, we will have the strictly positive eigenvalues coming from each component. But unfortunately, we will obtain at least one eigenvalue of this auxiliary form that is now 0. This is because we take this orthogonal sum here. That means we have a lot of eigenvalues where lambda is strictly positive, and this complete thing is completely positive, is strictly positive. But we have at least one eigenvalue where lambda is negative, and so this complete thing up here is where lambda is 0. So this complete thing up here is strictly negative. And if we have positive and negative eigenvalues of the Hessian, we have found a saddle point and not a local maximum. Now, this only works for large alpha, but we did a lot of numerical computations for different alphas, and it seems to be true that these lattices are just saddle points regardless of how big alpha is. We just didn't prove it in detail. because this is what we really were interested in. So we know everything about all even unimodular lattices up to dimension 24. None of them are local maxima, but we know exactly what happens. So what we accomplished so far is that while searching for a local maximum of this function on this manifold of rank n lattices with point density 1, we had no luck up to dimension 24. I said in the beginning that we had a candidate for which our first numerical computations looked nice. This wasn't in dimension 8, 16, or 24. This was actually in dimension 32. And it turned out in the end that the lattice we looked at was completely the right one. It was a local maximum. We just looked at the wrong parameter alpha. And this was very unfortunate. Or maybe fortunate, because if we would have seen this directly, we would have never done everything I told you so far, because we would have been done. This would have been a 3-page note or something. But in the end, it worked out. And we didn't find one local maximum, we found millions of them. The reason is the following. We take a look at even unimodular lattices in dimension 32 that have no vectors of squared length 2. Any such lattice, as is known, has the same theta series. So these are different, not isometric lattices, but they all share the same theta series, just by the fact that they don't have vectors of length 2. And there are at least 10 million such lattices. What we know is that all shells of such lattices form spherical 4 designs. So in particular 2 designs, they are critical. This was the reason why we started to look at them, because if all shells form spherical 4 designs, the computation of the eigenvalues becomes drastically more easy. That's not correct, but works for now. Because this polynomial that was a problem had degree 4, and now we have 4 designs, so everything becomes nice. And in fact, there will be only one eigenvalue of the Hessian. If you choose the right basis, it will be a diagonal matrix, a multiple of the identity matrix. Maybe not a big surprise if you play around with these kinds of sets. Otherwise, you can just do the following computation, which is not from us, but from Renaud-Coulagent. It's quite old at this point. What you just have to do is you have to realize that the Hessian simplifies to this object if all shells are 4 designs. And then you choose an orthonormal basis of traceless matrices, traceless symmetric matrices. Then because the inner product of H with itself is just the trace of H squared. If you fix this to be 1, then here is just a 1 and everything on the diagonal is the same. And if you have 2 different vectors, you're on the off diagonal, it's just 0. So everything is super nice. And instead of taking this big expression for the eigenvalues we had before, we can now work with this expression with the 1 here instead of the trace of H squared. We only have to evaluate this series to make everything rigorous, or to do numerical computations. And it looks like this. If you compute the eigenvalue for alpha at least pi, remember it's symmetric around pi, then from this plot, we see that for a little bit around pi, it will stay negative. We will have a local maximum, and then it will become positive, and it will stay positive, even though it approaches 0 really fast. Our problem was that when we initially started these computations, we didn't think too much about this point of symmetry pi, and we just ended up outside of this little area with all our computations we ever did. This was unfortunate, of course. But as I said before, our numerics betrayed us, so we wanted to make this rigorous. And I would like to show you that this is actually possible. What we did is we just took alpha to be pi, the point of symmetry. We took this formula for the gradient, for the Hessian, for the value of the Hessian, and we just computed it up to a certain precision. And so this is obviously a negative number. Then we tried to bound the remainder of the series. And we were able to do this. There's a rigorous proof for this bound. And this number here is small enough that it can never interfere with the sign up here. So whatever this actually is, the complete series is negative. To do this, you need something I would call modular form magic. You need to remember that your theta series are modular forms, and you will just write down your theta series explicitly as some very specific modular form, an Eisenstein series, plus something that is, again, a cusp form. So a modular form for which in its Fourier expansion, the constant coefficient is 0. If you do this, the AMs from before, the coefficients of the theta series, will be just BM plus CM, and we can bound each of them separately. The coefficients of the Eisenstein series are known explicitly by some divisor power function and Bernoulli numbers, and they can be bounded by some polynomial expression just by using well-known bounds for this divisor power function coming from number theoretic arguments. It's related to the Riemannian zeta function. So this is very explicit, very nice. The cusp forms are more complicated, more involved. But fortunately for us, as I said before, modular forms is something people really like and have done a great deal of mathematics with. And Jenkins and Rouse produced a concrete bound for the coefficients of cusp forms in the case we need. I don't know how your mathematical taste is developed. To me, this is usually not a nice expression. I would stay far away from this. But here it is a nice expression, because if I fix the lattice, which I have done, everything up here is a constant I can just read off somewhere. This L or this K, these are just numbers we can pin down if we know the lattice. And then this is just a complicated way to write some number, and we just bounded it by something reasonable. Or maybe not even reasonable. I'm not sure. This bound here works. I don't claim that it is good. The interesting fact is that, again, this is just a polynomial. It's just, again, a power of m. It looks the same as the thing we had before. And this we used by now putting everything together, bounding the BM and the CM part of AM separately. We obtain one series involving this power of m. We obtain another series involving this power of m, but they look super similar. And this is the only place where infinity is still a problem. It's the only thing we still have to do. And with a finite little trick from calculus, we were able to argue that this series, in fact, is basically just an incomplete gamma function, and we can evaluate it. Now, just have to do a bit of calculus. It's not hard, it's not nice, but it's calculus. You can do it, and you get concrete numbers that make everything finite, and you obtain these numbers on the right side. And if you now evaluate everything, we have the bound I promised you before. Everything becomes super explicit, super rigorous, and we should be able to enjoy this. All right, I took a bit more time to explain some things in the beginning. So I would just say at this point, we have a local maximum. We are very happy with this. And I do thank you for your attention, and we'll just be finished with my talk right here. Thank you.
All right, thanks, Mark, for a very nice talk. Let's take a moment to click our satisfaction, clap with the reaction button at the bottom.